So in this video, we're going to start looking at work and the way that we can calculate work in systems that are interesting to chemists. So you'll remember that we've been talking a lot about energy, and we have this important law about energy, and it's called the first law. So let me just remind you of that. So one way of writing the first law of thermodynamics, remember the first law tells us that energy is conserved. Another way of saying that is just looking at the ways that energy can go into or out of something. So we can say that the change in the internal energy E of our system, well, it can only change by two ways. Now, energy can't be created or destroyed, but it can be transferred. But how can it be transferred? It can be transferred by heat, which we're going to call Q for heat. I know it doesn't sound like it. Q has anything to do with heat, but that's just the term that we use. So we're going to add up the total amount of energy that gets transferred as heat into or out of our system, and we're going to combine that with the total amount of work done on or by our system. So those are the two ways that we can transfer energy, via heat and via work. So this video is all about this part. So how do we figure out what that is? Well, let's imagine that we have this kind of process going on, because this is the kind of process that we as chemists are mostly interested in. So this is called expansion or compression work, and this happens whenever a system changes its volume because of some reason. So we're going to imagine that we have a can here. So that's what I've drawn here. I know it's a little bit warped, but anyway, so there's a little can here, and we're looking at it side on. Okay, so there's a can that I've drawn. Now inside this can, we're going to put a movable wall. Technical term for this might be a piston. So here's a little wall. I'm going to draw that in there, shade it in. Alright, so this wall, we imagine, can move up or down. So this is a movable wall. Okay, so that's a piston. Now also on this wall, sitting on top of this wall, we have a mass, a weight. So I'm going to draw a little picture of a weight right here. Alright, so this weight is pushing down on this piston with some force, right? Because it's got some force, it's got some mass, gravity's pulling that mass down, and so it's pushing down, weighting down that piston. Now that force gets spread out sort of over the whole area of this piston, because it's not just at one point that we feel that force, but everywhere along the inside of that piston. And so the force per unit area is called a pressure. We're going to talk more about pressure in a later video, but for now just know it's the force that's pushing down on something. So that's the pressure. And we're going to call that P sub EX because it's an external pressure. So inside here, what do we have going on? Inside here we've got a gas, let's say. So here's a gas. I'm going to draw some gas molecules. So here's some gas molecules, and they're buzzing around in there. So we've got this gas. Now we're also going to imagine that we've got this piston. We're keeping it from moving because we've got these little stops in place. So I'm going to put some of these little blocks right here, and that's going to keep our piston from going up. Let's say that these gas molecules, this is a gas under pressure, and they're trying to push up on this piston, but we're going to keep it from going up. Okay, so now we're going to imagine a process that happens. So here's my arrow representing a process. And what we're going to do is we're just going to remove the stops. So pull out all the stops. And what happens? Well, because this gas right here is at higher pressure than the pressure pushing down on this weight, the piston is going to move upwards. So we have an expansion going on. So let's draw the final state over here. So now what's happened is our piston has gone upwards. So there's our piston, and we've got some new volume. Now our mass is still here. So let me draw our mass back in here. And it's still pushing down on that piston with that same pressure. That pressure has remained constant during this whole process. And now we've got this gas a little bit more spread out, so it's a little bit roomier in there. So that gas now has more space to move around. Okay, so we've had an expansion. We've gone from some initial volume, so we'll call that V sub I for initial, to some final volume, V sub F. And so we call that an expansion. So how has the work been done here? Well, let's think about it. We've got a mass here, right? And that mass has now been lifted to some higher altitude, right? It's higher above the surface of our tabletop here. And we know that as you move higher, your gravitational potential energy increases. Remember, we had this formula for potential energy. It says that potential energy is equal to the mass of an object times the acceleration due to gravity times its height above some arbitrary reference point. And so we have pushed this mass upwards. So if the gas here, the stuff inside this can, is what we're going to call our system, then the mass that's out here is part of the surroundings, as is the piston and everything else. So what has happened is we've moved a mass in the surroundings upwards. And it takes work to do that, right? Let's think about that again. So the height has increased. So what has happened to the energy of this mass? Well, it's gone up, right? So it now has a higher energy than it did initially. Where did that energy come from? Well, it must have come from the system. So what we say in this particular example for an expansion, so I'll just abbreviate that EXP, that the system has done work on the surroundings. So I'm going to underline on. All right, so the system has done work on the surroundings. How do we know that? Because a mass that's part of the surroundings has been moved to higher energy. Where did that energy come from? We can't create it from nowhere, right? So it has to come from somewhere. So it could come from somewhere else in the surroundings, but that's not where it came from, because we see that the system has also undergone a change. So the system has lost energy, and that energy has gone out into the surroundings. So we're conserving energy. So we would like to calculate now how much work was involved, how much work was done by the system on the surroundings. And to do that, we need a formula. So I'm going to scroll down here. All right, so here's our formula. So under conditions of constant external pressure, I'm just going to abbreviate that, constant, C-O-N-S-T. So we've got this constant external pressure. So as long as that is true, it's supposed to be dot, 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 we can use this formula. We can say that the work done on or by the system is equal to negative P external, so whatever our external pressure is, times delta V. Now you'll remember that delta is the symbol that we use. This is the capital Greek letter delta, and it's the symbol that we use for change. So anytime something is changing. And it's always thought about as the change from the initial state to the final state. So delta V will be the final value minus the initial value. So this whole term right here, we can rewrite that as VF minus VI. So the initial volume minus the final volume. And that's how we can calculate the work that gets done. All right, so let's think about this with two example problems. So we'll look at that next. So here we have an example problem that's going to put together some things that we've been talking about. So in this case, we're trying to look at this example of a cylinder. Right, so we've got a cylinder, a can, and inside that can there's this piston, so this little piece of metal that can move up and down, and it's attached to this rod. So this is what's going on inside your car engine, an internal combustion engine. So we insert fuel and air, and then there's a little spark that causes those gases to react. There's a combustion reaction that takes place. And so in the course of that combustion reaction, we're going to release some heat. So we're going to release some heat to those gases. It's going to make those gases hot. Those gases are then going to expand, and as they expand, they're going to push down on this piston. So pushing down on this piston, they're doing work on it. And so then this piston is going to push a rod, which pushes some other stuff, and eventually turns the wheel of your car. So the gases expand like this. So we want to calculate what is the change in the internal energy of the system for this process. So that's our goal here. So what do we know? It says the gases expand, and as they expand, they do 93 joules of PV work. So in the last part of this video, we talked about what PV work is. It's expansion compression work, and we learned a formula for calculating that. So in this case, we're just told how much is done. So the gases expand and do 93 joules worth of work on that piston. So there's also this combustion process that takes place, and when that combustion reaction happens in here, that's our system, the gases, that energy is going to be transferred to the system, so it's going to stay in the system. It's going to heat those gases up. So how much energy gets transferred? 155 joules of heat energy goes into the system from this chemical reaction. And so we want to know what is delta E for the system for this process. So we can work this out by starting with our first law statement that says that delta E, that the only ways that you can transfer energy to the system are through heat, Q for the system, and work. So now we know up here heat, so there's our heat energy, Q, and right here is our work, W. So all we have to do is put them in this formula, but we have to be really careful about our sign convention. Okay, so remember our sign convention. We're going to have a positive sign anytime energy goes into our system, and we'll have a negative sign anytime energy goes out of our system. All right, so let's think about Q. It's 155 joules. Is that going into our system or out of our system? Well, that heat is going into the system to make the gases hot, right? So that heat is transferred to the system. So it gets a positive sign. So that's a positive 155 joules of heat energy. So there's Q. So now we're going to add to that W. So what is W for this process? So we're told that gases expand, so they're going to do some PV work, and they do the work on the piston. So they're pushing this piston to a different position in terms of energy. They're moving a mass somewhere in the surroundings, and that takes work. So the system is doing work on the surroundings. So I'll go ahead and write that down here. System does work on the surroundings. So the system does work on the surroundings. So that means the system is losing energy. So some of this energy that was in this hot gas is lost because it's doing work by pushing that piston out. And so it's losing energy. We give that a negative sign. So that's very important. Whenever we do work on the surroundings, when the system does work on the surroundings, it's going to get a negative sign. So that means somewhere in the outside world, energy is increasing. We're taking that energy out, we're using it to move the car around, right? So that's going to get a negative sign. So a negative 93. The system has lost some energy due to work. That work is going out into the surroundings. So now all we need to do is the math. Do the math. 155 plus a negative 93. That gives us a total of 62 joules. So from this one stroke of this piston, the change in the internal energy here is going to be 62 kilojoules. And that's positive. So inside this system here, we have gained that much energy. So we started at a lower energy, and we have now gone up in energy. So most of that energy you see has come in the form of heat. And then we lost a little bit of that total heat energy by doing this work. So there's still a lot of heat energy, thermal energy that's in here. If we cool that system then back off again, we can take that heat energy out and dump it into the surroundings. So in this example problem, we're going to try using our formula for expansion compression work, also known as PV work, to solve this problem. So here in this problem it says that balloons are inflated from a volume of 0 liters, right, so they're empty, to a final volume of 4.8 liters on a day when the external atmospheric pressure is 1.01 atms, or atmospheres. How much PV work is done by 100 balloons on the surroundings when they are inflated? So let's just think about what that means, right? So we've got this balloon here. And as we inflate it, right, the external atmospheric pressure is pushing down on it from all directions. And so as we inflate that, we have to, the balloon is having to push that outwards. So the balloon, our system, the gas in the balloon, is doing work on the surroundings by pushing it outwards. So that's what's going on, right? So as we inflate that balloon, we're continuing to push the surroundings, all this gas and stuff that's out here, we're pushing that outwards. And this gas is pushing down with a constant external pressure of 1.01 atmospheres. Alright, so since we've got a constant external pressure, we can use that formula that we derived last time in class. Or didn't derive, we presented it. So work is equal to minus a negative sign, P external times delta V. So remember this minus sign that's out front here, that's pretty important. That's to get this formula to agree with our sign convention. That is, anytime energy leaves the system as work, it's going to get a negative sign, and anytime energy comes into the system as work, it's going to get a positive sign. So now we just need to carefully put in our numbers. So our external pressure is 1.01, and then we're going to multiply that by delta V. So delta V, remember delta always means final minus initial. So we're going to do our final volume, and so it says we're expanded to 4.8 liters. So I should point out that by doing it this way, I'm going to calculate the work done by one balloon. We actually says in the problem that we have 100 balloons. So when we're done with this calculation, what are we going to have to do? We're just going to have to scale it up. So we'll know how much work is done by one balloon. If we've got 100 balloons, we just multiply. So here's our final volume, 4.8 liters, and we start with an initial volume of 0 liters. So when we're done with this calculation, we get a value of negative 4.80 atmospheres times liter as our unit. Alright, so that's the amount of work, and work is a way of transferring energy, and this is the work that has been transferred from the system, done by the system, on the surroundings. That's why it's negative. So the negative sign means that we've done work by the system, on the surroundings. So I'll underline by and on. By the system, on the surroundings. So this is kind of a funny unit, an atmosphere times a liter, because we know that work is a way of transferring energy. So it must be that atmospheres times liter is a unit for energy. And it is, but it's not a common unit. So we would like to convert that as kind of our last step into more common units for energy. So I'm going to scroll down here a little bit. So it turns out there is a conversion factor. So 101.325 joules is equivalent to 1 atmosphere liter. So we can use that as a conversion factor to convert our value here. So we've got work is equal to, but before I do that, let's go ahead and scale this up. So we've got 100 balloons, right? And so each balloon does this much work on the surroundings, negative 4.80 atmosphere liters. And so that equals, we're all done, negative 480 atmosphere liters. Now we're going to convert that, negative 480 atmosphere liters, and we're going to use this conversion factor. So we've got 101.325, wow, what happened there? 0.325 joules per every 1 atmosphere liter. So I put that atmosphere liters again in the denominator, so we'll divide out the atmosphere liters up here, and then I'll get my answer in joules. And so when you do the math there, that works out to be negative 4.9 times 10 to the 4th joules. And that's equivalent to negative 49 kilojoules. So there's 1,000 kilojoules in 1 joule. So there's an example of how we can use our formula to calculate the amount of PV work done when a system is expanded. In this example, compression would be exactly the same process, except we'd be going from a larger volume to a smaller volume for our system. And so same process, same formula.